For number 1, we're going to find the critical value needed to form a confidence interval at a specific level of confidence. In this example, it's saying the confidence is 0.91. Confidence intervals are discussed in chapter 6.1. And I'm going to this page to show a visual picture of what we're trying to find. If we want to have a confidence interval with 91% confidence, we would want this shaded in part to be 91% of the normal distribution. So we're trying to find the critical values, and they're symmetric here around the mean. So the critical values that have 91% of the distribution in between them. Well, in this example, if there's 91% in between, that means there's 9% split between the tails. So 9% divided by 2 is 4.5%. So there's 4.5% in each of the tails if we have 91% of the graph in between these critical values. And we can use this formula in Excel to find the critical value associated with a specific probability in the tail. So if we want there to be 4.5% in the tail, write that as a decimal, 0.045, and it gives us the critical value we need so that there's 4.5% in that tail, 4.5% in that tail, 9% total in the tails, and 91% in between the two critical values. Number 2 is similar to number 1. We're looking for critical values to create a confidence interval, and our level of confidence in this example is 0.92, 92%. Well, if there's 92% in between the two critical values, that means there's 8% in the two tails. And 8% split between two tails, 8 divided by 2, would give us 4% in each of the tails. So we're looking for the critical value that has 4% in the tails and then 92% in between the two critical values. So use this formula in Excel. We want 4% to be the amount in the tail. So this is the left-hand critical value, negative 1.75. And then positive 1.75 would be the right-hand critical value. And there would be 4% in each of the tails and 92% in between those critical values. And number 3, we are going to construct a confidence interval for the population mean. We're going to get a range of values that we're confident the population mean lies within. And to do this, we gather a sample of data from that population. And we have information here on that sample. It's of size 50. And the sample mean is 8.5. And now we're also told what the population standard deviation is. And that's very important. It means we're going to use the normal distribution. And this says we're going to look for a 90% level of confidence. And this is discussed in chapter 6.1, how to create the confidence intervals. It all hinges on the central limit theorem. We know that when we look at samples of size above 30, the means of those samples will follow a normal distribution. And so that's going to allow us to create a confidence interval. We're going to center our confidence interval around the sample mean, and then this formula tells us how to get the margin of error, which lets us find the upper and lower bound of our confidence interval. We can let Excel do all the math for us. The key thing we have to recognize, though, is that this is a situation where we know the population standard deviation, and when that's the case, we're going to use the normal distribution, and the formula in Excel is confidence.norm. So alpha is going to be our 100% minus our confidence level. So confidence level of 90%, we would want 10% as our alpha. The population standard deviation was stated as 0.8, and the sample size was stated as 50. So if we type those in, Excel gives us the margin of error. Now, to form the confidence interval, the sample mean is always right smack dab in the very middle of our confidence interval. And then we add the margin of error to the sample mean, and that gives us the upper bound of the confidence interval. And we subtract the margin of error from the sample mean to get the lower bound of our confidence interval. So we're 90% confident that the population mean lies somewhere between the lower bound and the upper bound. 4 is similar to number 3. we're finding a confidence interval for the population mean, and we have information about our sample. We have the sample mean and the sample size. We're also told the population standard deviation, so we know we're going to use the normal distribution, and we want a 90% level of confidence. Because we know the population standard deviation, we can use confidence.norm. We're using the normal distribution. Here's the information we have, and we enter it into that formula, equals confidence.norm. Our alpha is 10%, 100% minus our confidence level, population standard deviation, and sample size. And Excel gives us back the margin of error. The sample mean is always right in the middle of our confidence interval. We add the margin of error to the sample mean to get the upper bound, and we subtract the margin of error from the sample mean to get the lower bound. And then our confidence interval, we're 90% confidence the population mean will lie somewhere between our lower bound and our upper bound. For number 5, we are going to set the parameters we want for our confidence interval and determine the minimum sample size that we would need in order to have those conditions met. So we want a specific level of confidence, and we want a specific margin of error, and we know the population standard deviation. This is discussed in chapter 6.1, and the formula is given here that we use. We plug in the values that we want, and we can get back in, which is our sample size we would need to have the conditions we want. So here is the information we were told that we wanted for our confidence interval. And the key thing we need to do first is convert this 95% confidence into the correct critical value. Like I discussed at the beginning of this video, we're looking for the critical values that there's going to be 95% in between those two critical values, 95% of the distribution, which means there's 5% in the tails. 5% total, which split between two tails, would be 2.5% in one tail and 2.5% in the other, leaving 95% in between the two critical values. So because we have the population standard deviation, we're dealing with the normal distribution. We want to use this formula, norm.s.inv, and we want to find the critical value associated with 2.5% in the tail. And we get that value from Excel. So now we use that formula to find the sample size that we're going to need. And that critical value we found is going to go right here in the formula. The formula said to take that critical value, multiply it by the population standard deviation, and then divide it by the margin of error. And we're going to take that whole result and square it. I think it's easier to type in Excel separately. So I've done the multiplication and the division, got my result, and now over here, I'm going to take that result and square it. You can do it all at once. You just have to be careful with your parentheses to make sure you type it in correctly. I like to split it up into 2 steps. So I'm squaring my result, and I get that my needed sample size would be 43.1. Now, if you're, imagine surveying somebody, you can't survey 43.1 people, but if you need at least that many, we would have to round up to 44 people. Always go up to the next largest whole number. You can't round down because we need more than 43. We need 43.1 at least, so 44 would be the smallest amount we could have in our sample. Number 6 is similar to number 5. We're going to find the minimum sample size that we would need to create a confidence interval to estimate our population mean. And we have the level of confidence specified, the population standard deviation, which lets us know we can use the normal distribution, and we have our desired margin of error for our confidence interval. We use the formula listed in 6.1 to find the sample size that we would need in order to create the confidence interval with the given specifications. So first we need to find that critical value. 98% level of confidence means we want to find critical values that have 98% of the normal distribution in between them, which would then leave 2% of the distribution to be in the tails, split between two tails. That means there would be 1% in each of the tails for a total of 2%, with 98% in between our critical values. So we need the critical value that's going to leave 1% in the tail, norm.s.inv with 1% in the tail of the normal distribution, and we'll get the critical value here in Excel. The formula for the needed sample size tells us to take that critical value, multiply it by the population standard deviation, and then divide by the margin of error. We're going to take that result and square it, and I just do that separately. I think it's easier to type into Excel. So that result squared gives us our needed sample size, and we need at least this many, so we have to go up to 251 to the nearest whole value larger than this, and so 251 would be the sample size needed. For number 7, we're given information about a sample. We have the sample mean, and we're told it creates a confidence interval for the population mean, and that's listed here. The question is it possible that the population mean, which we're confident is somewhere in between these numbers, is exactly equal to the sample mean, which is exactly smack dab in the middle of our confidence interval? Well, that is going to be very unlikely that our sample mean exactly lines up perfectly with the population mean. We're just confident the population mean is somewhere within these numbers. And since this is actually a pretty wide range, it's even more and more unlikely that the population mean would exactly equal our sample mean. For number 8, we have information about our sample. We have a sample mean that's going to go right in the middle of our confidence interval, and we're told that this is the lower and upper bound of our 95% confidence interval. So we're 95% confident that the population mean lies somewhere in between these values. Question is, does it seem possible that the population mean could be greater than 91 degrees? Looking at our confidence interval, this does not seem possible because 91 is greater than the right endpoint, the upper bound of our confidence interval. Number 9 is asking if everything else remains the same, how will changing these factors affect a confidence interval? The first one is increasing the level of confidence. If we increase the level of confidence, it's going to widen the confidence interval. That's because if nothing else has changed at all, the only way to get more confidence is to make your interval that you're guessing the mean might lie within even wider. So it contains more numbers. There's a higher possibility that it will actually contain the mean. So you get a wider interval gives you more confidence. What happens if everything else stays the same and we increase the sample size? Well, we're going to have more accurate information with a larger sample size so we can make a more narrow and precise confidence interval. If everything else stays the same and we increase the population standard deviation, if that increases, that just means the data is more spread out, and with more spread out data, we're going to end up having a wider confidence interval trying to estimate the population mean.